So, let's start. So welcome everyone to the Stockholm NLP Meetup, actually our fourth meetup. And as you already know, it's about the word embedding from theory to practice. And first of all, I'd like to thank our host, Gavagai. Well, I did all the talking and the conversations with Magnus. Thanks a lot, but I'm sure everyone helped a lot in Gavagai, so thanks everyone. And so let's see what all these discussions that we had and with Hendrik, Jimmy, and Magnus, how it's going to be. So I put some also history slides. This is the lesson I learned from previous meetups that we had, that there are many people that come new, so we should have some reminder of what we are actually doing. So the first meetup was in October. What technology requirements should we pose and big data analysis tools? And our presenter was Lucy Heuer, and then we had in December the main entity recognition, challenges, solutions, and applications. That was presented by me and Basta. And then in January we had the NLP and deep learning introduction session 1. We will have a session 2, and that was presented by Roloff. Now we actually have a deep learning sister meetup, and then this is a plot of what has been going on in our meetup, and you see that it does have some nice patterns, and you can probably guess what is going on in each of the curves, so to speak. And it's not exactly as you expect. The first two ones, the first uprise is our meetups. The second one is a little bit afterwards. This indicates that we had an active interest and discussions in the deep learning related meetup. And then, now we are again going up. This means that we have our next meetup, and now we are 174 people. So we are a little bit behind the schedule. Sorry, there was some problem with the network and online streaming, but it's fixed. So today we have 3 talks. We need to be a little bit, on schedule from now on. The first one is Distributional Semantics at Gavagai. Then we have the work effect from theory to practice. Combination. The first one is more political and work around that, and also about Gavagai. The second one is a mix of theory and practice, and the third one is more practical. Then, also a little bit about our talks. The first talk, Distributional Semantics at Gavagai, is presented by Magnus Sahlgren. Magnus is chief scientist at Gavagai, also a co-founder. Hendrik presents the second talk, Work to Break from Theory to Practice. And Hendrik is also a master's student at thesis, almost finished with the dissertation. And so basically he's going to present his efforts on the dissertation. And I really like to thank you, Hendrik, because we had this discussion in the previous meetup. You got volunteer and suggested that you can present, and that was a really nice thing that I would like to see in these meetups. And then the third one is by Jimmy. Jimmy, I checked your LinkedIn profile. I'm not sure about your title, but I wrote language technologist at Gavagai, so correct me if it's wrong. And it's about distributional semantic models in practice. And let's start. The word is yours.
So thanks for the introduction. So my name is Magnus. We're here at Gavagai. I thought I should say a few words about Gavagai before I go into the topic of today's meetup, which is word embeddings, or as we like to call them here, distributional semantic models, and explain the difference in terms. But Gavagai, so this is our office. It's a very big place, as you can see. It's our third office in 5 years. By far the biggest one so far. It's actually way too big for us. So we even have an exercise room down here. But it's nice now that we can fill the room finally. So Gavagai started out as a spin-off company from SIX, which I think you're familiar with, Swedish Institute of Science. Most of us who work here has been at SIX in some form. And what we do here is, well, text analysis in general. And more specifically, we focus on doing text analysis for big data. So in scenarios where you have really large amounts of data, or if you have data that have qualities that make your normal processing tools less suitable, that's where we think our techniques are useful. So text analysis. We work with online data a lot, so social media data from that's the main data that we process. Screens behind me show some of the processing things that we do. So our production system on that side and the stage system. So we develop a number of different systems and applications. We have something called the Monitor, which is a tool for social media monitoring. It's available at monitor.gavagai.se. You can go there and find out. And then we also have a tool for multi-document summarization, which is called the Explorer. And that's available at explorer.gavagai.se. So for example, if you have like product reviews or some other very and explore the data set using this tool. And then we have another system which we are actually demonstrating for the first time today, which is the Lexicon, the living lexicon, which is available at lexicon.gavagai.se. We haven't really released it yet, so it's still in beta, and this will be the first public appearance. I'm very excited about it. It's our core production distributional semantic model live on the internet. And all these three systems are built on top of our API. Everything uses our API, and if you're a developer and you want to build your own stuff using our API, we encourage you to do that. You can go to developer at developer.gavagai.se and sign up and start hacking away. We will be very happy for that, and any feedback that you have regarding functionality or the API itself would be very much appreciated. Right, so a lot of the things that we do here on Gavagai sort of focuses around these type of models that we've been talking about here. We like to call them distributional semantic models. There are lots of terms that are being used for these type of models. So, word spaces, or semantic vector spaces, or semantic memories, or word embeddings, but they're all really referring to the same type of models. Namely, computational models that implement a set of assumptions and hypotheses about the nature of language and the nature of meaning in language, which we call the distributional hypothesis. And I like to go on and on about this because I think it's important to understand the linguistic theories behind this. But basically, you can sum it up with the following thing here. So this terms with this similar distributional properties and similar meanings. So that means that if you have a data set and you can collect distributional patterns of words in that data set, then you can use those distributional patterns to quantify semantic similarities. That's the distributional hypothesis. And you read papers on these models, you see this quote in almost every paper, but there is really no reference for this quote. So who said this? Do you know who this is? Anyone recognize this? That's a very good guess. This is Sally Harris. Sally Harris was Chomsky's teacher. Yes, it is actually from the same base. Yes, no. He didn't say this. He didn't formulate the distributional hypothesis, but he proposed a distributional methodology for linguistics. He was very concerned with linguistics as a science. How can we make linguistic investigations scientific? And his idea was that, well, we can't study linguistics using language because that's the sort of object we're studying. So we must use something else. His proposal was distributional facts. And this whole sort of field of models comes from this one. So let's skip the theoretical part, and let's skip the linguistic part, and let's go into the actual models now. So they're actually quite simple. At the heart of all these models, you find something that we call a co-occurrence matrix. This matrix is a representation of the data such that we have the vocabulary as rows of the matrix here. So each of the term types in the data has its own row. Or if we're only interested in the subset of the terms, we call them target terms, and they have terms. Then as columns, we have the contexts in the data. And what that can mean, we'll come back to that. And then we simply populate this matrix by noting co-occurrence events. So whenever a word occurs in the context, we add a 1 in the cell. So we populate the frequency matrix. Very simple thing. And this means that word number 1 has occurred 1 time in context number 2, word number 2 has occurred 1 time in context number 1, and 2 times in context number 3, etc. Very simple representation of data. Now, of course, we don't normally just use frequency counts because of the fact that in language we have terms that are very promiscuous. They co-occur with many words, not all English. They're not really contributing to information. So we like to quantify the importance of co-occurrence events. And we do that by using some form of term weighting, like an association measure. And I'll mention some of these. So these are quantification of the importance of the co-occurrence event. So this one is a really important. Okay, so the point of doing this very simple representation of the data is now we can interpret the rows here as distributional vectors. So it's a representation of the distributional pattern for the word question. So what is the point of doing this now? Well, if we have two words that have occurred in similar contexts, they will get similar distributional vectors, and then we can use these vectors to quantify similarity. Quite simple and it works. So you note that the only really important aspect of these models is the actual pairwise similarities between these vectors. The vector similarity is what we want to obtain. And I think this is a very nice quote that sort of defines these models. Vector similarity is the only information present in the workspace. Semantically related words are those unrelated words of this type. This is from Linus Schutz's very influential paper Workspace back in 1992, which is sort of the paper that led to the whole field. And his idea was this. This is actually from another one of his papers from 1992. So this is a workspace. And of course, it's very intuitive, and you all understand the point of this representation. So words that are more similar to each other are closer in this space. Words that are not so similar distant. So here you have like microprocessors and things like that, and then you have technology and stuff like that. And this is, of course, built from this huge dimensional distributional space projected down to 2 dimensions. And we'll see Hendrik give us some more examples of that later. Right. So these models, they differ with respect to a number of parameters, of course, how you do the frequency weighting, how you calculate vector similarity. But the most important thing is how you define contexts. That is the only thing that will decide what type of similarities you will get in the model. There are basically two options. The first option is you can use documents as context. And for those of you who work with information retrieval, you will realize that this is just a simple vector space model of information retrieval. It's a standard vector space model. So you have your terms as rows, and then you have documents. This is like an inverted index. Now, when we work with a vector space model, we typically use TF-IDF to do the frequency normalization. It has been referred to as simple proven measure, and it's really hard to optimize on. So don't try to do that. Just use TF-IDF. Will give you optimal results. And of course, the point here is that we can now compute the similarity between terms that have occurred in the same documents. So if you, for example, would produce one of these vector spaces based on my academic papers, for example, you will see a similarity between the word matrix and the word semantic, because they often occur in the same documents. Right. Now, that doesn't mean that matrix and semantic mean the same thing, but they are topically, they are about the same topic. So using this model, we can sort of quantify topical similarity. And of course, that's very useful when we work with document processing and information retrieval. Then what we want to capture is topical similarities. It's a good model for that. The other type of model is to use terms as context. And in this case, we would have a symmetric matrix. So we have the same entities as rows and columns. And in the worst case, we have the vocabulary times the vocabulary. And then we simply note when terms co-occur together. So if I say I drink coffee, then I add one there and I quantify it. And you realize now that what we're capturing now is something that we call also second order co-occurrences. And I should also mention that the standard way to quantify importance of co-occurrences in these type of models is using the pointwise mutual information, which is this one. I think Jimmy will talk more about PMI. Yeah. There are tons of variations of the PMI measure. You can add constants here and there, and you can subtract constants. The latest development is called shifted positive pointwise mutual information, which subtracts it into constant. And it improves the results enormously. But of course, the point of this representation here is we capture second order references. So terms that co-occur with the same other terms get similar representations. So in this example, if I have coffee co-occurs with drink, and tea co-occurs with drink, and coffee and tea will get similar vectors. And this is semantic similarity. This is the definition of semantic similarity in linguistics. The terms are substitutable for each other in context. So in linguistic models, it's a paradigmatic relation. And all lexical semantic relations are paradigmatic relations. So this is a nice model if you're interested in semantics. So this is really the most important thing you should remember from this talk. If you use documents or text regions as context, you can capture topical similarity. If you use terms as context, you will get a semantic model. Right. So far we've been talking about the basic model, and I need to speed up. I realize I just want to mention some of the basic models that people use out there. I'm not going into any details here. The first model that was developed was called latent semantic analysis or latent semantic indexing. It's the same model. It uses the vector space model. It was developed in information retrieval as a tool to handle synonymy problems. And then it doesn't use TF-IDF, it uses entropy-based indexing. And then it reduces the dimensionality using matrix factorization technique called similarity composition, actually truncated similarity composition. And the reason why you do that is you infer second-order relations in the vector space model. So you sort of approximate semantic similarity. That's very useful in information retrieval. The other sort of basic model that was around at the beginning of the 90s was called the hyperspace analog language. It was a word-based model. It was developed in cognitive science. And it has this very nice feature that it encodes directional occurrences. So the rows and the columns of the matrix will represent concurrences to the left versus the right. And that is kind of nice if you're a linguist because it represents at least very simplistic form of wording. But of course, when you want to use these vectors, you have to concatenate them, which leads to very, very high dimensional vectors. So from a practical perspective, this is really intensive. Then I'm sure some of you are familiar with topic models, which latent conditional allocation is a standard one. Was basically developed as an extension or probabilistic alternative to SVD. So instead of using the quantitative SVD, you use a probabilistic mixture model. Very and these are called topic models, which is very fitting because they're using documents as context. So we capture documents in that. Now we come to this term word embeddings. And the point with word embeddings is that okay, instead of just accumulating concurrence counts in one of these count matrices, we can actually produce one of these matrices by using a neural network. And we optimize the network for some type of prediction task. This most widely used prediction task when we talk about this context is sequence prediction. And that also means language model. So you have an input sequence and the task of the network is predict the next token in the sequence, or as you will see, the next sort of context. This is not really something new. It's a very old concept. It was used all the way back in 1990 by Jeff Ellman and his simplified networks. And he actually built a language model based on a simplified network. So the task of his network was to predict the next token in the sequence. And he realized that if you would take the hidden layer, it was just a one layer in this network. If you take the activation in the hidden layer and average that of all occurrences for a term, you would actually arrive at a very useful distributional representation that could sort of replicate the semantic classes of input data. And then it was realized by some commentators on the plate a few years after that you could actually arrive at the very same result even without training the network. Just the averaging of context will give you that result. And so that's equivalent to using the concurrence matrix. There are both deep and shallow architectures in this word embedding field. I think t-SNE is one of the first examples of deep architecture, uses a convolutional network consisting several layers. And then there are some shallow methods like Gavagai, which Hendrik will talk about soon. So I'm not going to talk about that at all. I'm just going to mention that. But for me, it's important to note that Gavagai is not really a model. It's an implementation. And the implementation features two different models. This continuous bag of words in the script. And it's been a lot of debate what the actual underlying model behind this implementation is. And there were some interesting results last year where Magnus Sahlgren showed that you can derive these models as an implicit factorization of the shifted point as a good point as mutual information matrix. So it's functionally equivalent to the count-based models that we talked about. So the latest model that was published last year is called Meetup. It's a very explicit word-based model using just the standard concurrent matrix. Very simple weighting scheme, taking the log of the counts, and then using regression techniques to factorize. And so, since we're back to using these concurrent matrices, and that's fine. They're producing great results in semantic tests, but they are computationally very intensive. That's a problem for us because we like to deal with dynamic streaming data, big data. So we can't really use these models in our scenarios. So the model that we favor here at Gavagai is something called random indexing, which was developed at 6 based on Hendrik Heuer's work on sparse distributed memory. I don't have time to go into any details, but Hendrik's model is sort of neurophysiologically plausible in the sense that it sort of replicates how the brain processes information. And the important aspect of this model is that the memory size of the model doesn't grow when we learn new things. It's sort of like the brain functions. It's not like the brain grows when we learn new things. Right? It's not the case that the one with the biggest head is really the smartest. But the brain makes new connections when we learn new things. So that's how Hendrik's memory model So basically the way it works is instead of us collecting this huge co-occurrence matrix, we simply accumulate co-occurrence counts in a fixed dimensional space where the number of dimensions is much, much smaller than the vocabulary. And it's a parameter, so it's a fixed dimensional representation. And we do that by incrementally adding sparse random vectors that represent the context. If you're interested in this model, we have published extensively, and you can read the details or you can ask me afterwards. I just want to show you a very nice video of how this type of model learns. Unfortunately, we haven't done the video. It's from Michael Jones in Indiana, but it's using random indexing. So here you have 3 different groups of words. You have countries, you have colors, and you have different types of fish. And here you will see the random indexing distributional vector here. And at the beginning of processing, you will see that it's just random, it's just noise. And then after a while, you see patterns emerge. And then you see a 2-dimensional scaling plot of the similarities here. So you will see it discovers the cluster structure. This is a very small amount of data. It's a balanced corpus of 10 million words. We start to process it. Everything just is random. There's no pattern in the vectors. Everything is just going haywire. This is the number of sentences we have seen so far. But even now, you see there's a slight pattern start to emerge here. We're just accumulating vectors here. We're not doing anything fancy. It's just counting. And now you see it has learned the cluster structure there. And basically, after we have seen like 5 million words, the clusters converge and not much else happens, because it's the same type of data. Okay. Cool. So we have learned the model. So that's basically how it works. And that's how it works in our production systems too. We're doing this operation all the time. As we speak now, the models are trained all the time. It uses a fixed size representation, so the size of our representations don't grow as we see in the data. It just projects it into this fixed dimensional space. And so if you would come up with a new term now, and you would start using it in blogs and Facebook and Twitter, our model would learn it. Because it's online all the time. It never stops learning. It doesn't do any factorization steps. And I'm out of time already, but I wanted to show you now this living lexicon. Great. Good. So I will show you this. So this is a web-based interface directly into our distributional memories in our production system. So as I said, it's still a beta, so we have released it. We have a number of different languages here. We have English, Swedish, German, French, Russian, Portuguese, Danish, Norwegian, Finnish, and Arabic at the moment. We'll be adding more languages as we speak. And just to show you how it works, this is everything that our production system knows about these languages, or about these words. And this is a live demo, so hopefully it works. Doesn't work. Ready? What is wrong?
I'm guessing it's a timeout.
No, we don't have any internet.
Around it 10 minutes ago.
Where is the network? There is no network. Oh, it's too bad. So, what you have to do is you have to try it out on your laptops, and I can show it to you later on. Yes, I know, but I don't have internet yet. And it doesn't.
Yes.
Yeah, yeah, but I don't find any networks. You know, internet. Mick is still in the house. No,
Someone stole your wireless.
So maybe we should just take questions. Because I can show this to you. Or do you have it? I did the internet.
Oh.
Yeah, the internet.
I mean, until this gets ready, we can start, with the questions, and then meanwhile this gets ready. Right? So, questions?
The matrix and model, how do you optimize this context part?
So the context part in a word-based model is about you're using what we call a context window. So it's a window that slides across the data. You're noting concurrence events within this window. And if you're interested in semantic relationships, it's the very closest context that is most informative. So the basic one that we use is 2 words to the left and 2 words to the right. That's the most informative context. And then you have models. I'm not sure if you're going to show some dependency-based models. Right. Because that's sort of an idea that you can restructure the context. Great. Okay, so yeah, was that so let me explain this lexicon here. So you enter a word, and this is everything that our production system knows about that word. And it knows several different things. It knows things that are string-like, similarly spelled. That's very naive. It's just a string similarity measure. But of course, it can be helpful to find morphological variants. Then it knows about some of the more common left side neighbors, so words that are left to the word, like civil suit and class action suit. And then you have right side neighbors, suit, jacket. And these are very noisy at the moment. And then you have some n-grams that the system has learned. This is a multi-word abstraction thing. We haven't told the system that it should have followed suit as an n-gram. It's something that the system has learned by itself. It's one of the salient n-grams. And then we have something called associations, which are like topical relations. And these are also quite noisy. But the most important ones are these, the semantically related terms. And these are the nearest neighbors in the distributional semantic model. And as you can see in our types of models, we do something called wordsmith induction. So the system actually learns several different meanings of the word. So it has learned the lawsuit meaning here, and suits, the civil suits. And then it has learned the sort of garment meaning of suit here too. The suit can be something that you actually put on. And these things here, they're sort of labels for these different meanings. And this is not something that we do externally to the distributional semantic model. It's a standard distributional semantic model. It's just a question of how we question the model. And that's a very common misunderstanding about these models, that they can't handle words that have several different meanings. They can. It's there in the model. It's just a question of how you ask the model to give the labels.
How do you get the labels?
Good question. So, so we're using random indexing. And random indexing mathematically, it's like sort of a hashing technique. So we project things down to a low-dimensional space. We can do that using hashing techniques. But the thing is that when you're using random indexing, you can reverse sort of the hashing. And that means that we can extract terms that co-occur frequently to the left and right. And that's the explanation for why these words are semantically similar. So this is a paradigmatic relation, and this is a syntagmatic relation. And this will not be possible if you don't have a model that can both give you substitutable and sequential relations. We're very proud of our model that it's possible to do here. We can just give you some other examples here. It's really fun to play around with. I hope that you will do that. I'm sure you'll figure it out. So So I think this is the first word people type into this type of system, just to sort of test if it has it learned the different meanings of apple. I know that this is the first word Fredrik always uses when he tests our systems. And lo and behold,
Killer instinct.
yes, it manages to learn the sort of fruit sense and the
You
Yes.
normalize?
Sorry? Yes, very good. I haven't tried it. It's a central bank.
But then you have two labels, those
Yes,
central.
yes. So we're working on it. This is something that we might change the way that we calculate the labels. We see
I think there's a ticket for it already.
it's on the board there. But, so it hasn't learned the riverbank sense.
Because of you don't have the data.
This is social media data. It's internet data. But we should also say that this is not the entire meaning structure of the workspace. This is just the top of the iceberg. So if you want to sort of dig into this, you can do that, but not in the web interface. So maybe we would be able to uncover that the riverbank sense further down the list, but it's not one of the salient meanings of the internet. I just want to show you one more thing. So one of the things that we use this type of system for is sentiment analysis. Because one of the problems when you do sentiment analysis on online data is that language use is very productive and people invent new words all the time. So it can be very useful to have one of these systems that give you new terms. So these are all things that Swedish people say when they think something is great. And they're quite good, good semantic neighbors. But you see here, and this is one of the reasons why these models are not really used that much in sentiment analysis, because they are paradigmatic relations. That means they will often conflate antonyms and synonyms. And if you do sentiment analysis, that's catastrophic, right? But this model has actually learned the whole cluster here with antonyms. So antonyms behave a little bit dissimilarly from synonyms. It's actually possible to separate. It's quite addictive once you start.
We have a bunch of languages that we don't speak, so maybe some of the people here can try some of the other languages.
Can you enter things in Russian? I don't really know.
Come to my computer with you.
Yeah, no, but we encourage you to use this and give us feedback on it. And we're the first ones to know about this lexicon, so we're very happy to get feedback on it.
But this says internet context. Have you like Wikipedia?
No, I don't think Wikipedia is in these workspaces. It's just online data.
I mean, if you use the Wikipedia as feed into system like this. Yes.
Oh, we have done it several times, yes, sure.
And if you look at antonyms in Wikipedia, that doesn't work. Or do you need a lot of more data?
So for the antonym detection part, I'm not sure, actually. I haven't looked at it in Wikipedia at all. Simply is an interesting question. But Wikipedia is very structured content. And I think, Jimmy, are you using Wikipedia in your demo?
No, I'm using
All right. Yeah. Because if you're using Wikipedia's data for one of these models, you get very good quality of the distribution representations because the language use is on editorial. But if you're using social media data, anything can turn up.
If you take a new political hype term like policy professional, in Swedish, policy professional,
Okay?
that's the same word in both languages. Well, what happens if you type the two words in Swedish or in English about the context or meaning? Because I think it's have the same meaning in one way.
Yeah.
but probably Swedes have a bit different understanding of the word than the original. I don't know, but have you tested that the words are the same?
We have looked a little bit at multilingual projections and seeing how things protect all the languages. We actually have a research project on political languages right now, where we are looking at languages, political languages across different languages. It's actually a research project. But I should also mention this thing about n-grams. So Swedish is a compounding language, and we tend to just form, real organizationer. We just add symbols. We don't use any blank space here. But it's okay, because in English, we will learn n-grams, and we will start indexing them as terms in their own right in the word space. So the model works well for these types of languages too.
Did you try Indian subcontinent?
Yes. We had Hindi previously in the system. I think we had Hindi. We didn't have Bengali.
It's probably getting online data. Even though there's a large population speaking those languages, there's not much because the language provider or the data providers are more of the very US.
So Fredrik is our data officer. He knows everything that is going on. But we are primarily focusing on European languages and going to the West rather than to the East. So Indian languages would be interesting to us too.
But if I understand, you have separate models for different languages.
Yes, we do. But you can, sometimes the language identification system makes an error. And so we have English terms in the Swedish workspace. And if you enter an English term in the Swedish workspace, you see that it has clustered all the English words together. Because that's the only thing it knows about.
Swedes also use mixing and other English words.
Theoretically, you could enter all the data into one workspace. The words would cluster into several different regions in the workspace. It wouldn't be a problem. But it's a bit cleaner to do this because you have terms that occur in the same string that occurs in different languages.
It would be interesting to see, like what you say, that certain words are used in a certain cultural context or language context. So there might be English word mixed with Swedish words in a different way than it's done by British people.
Oh yeah.
And you would end up that they would actually take place in different places, and they could be actually comparable in the same way.
Yeah, I think you can look that up like now. If you look at English slang terms that we use as Swedish, you see that it's used in a lot different way than in English.
Like tuxedo or smoking.
Probably.
So in your Apple example here, it seems like you normalize case before the system. You lose a lot of information there, right? Apple with a capital A is almost always Apple the company.
Yeah,
What was the basis for your decision?
Sparse data. We just want to have more data. Normalizing things. So theoretically, I think the representations would be better if we didn't do that. But we would, not get as much information for each string. So it's just a simple statistical reason. Want to add something?
Or just try one more search in Swedish.
Oh, I can't.
You have to reset the model if the language changes?
No, it's incremental. So it learns all the time. So we could actually do that experiment now. So if we would invent a word here on the Meetup, and everyone would start writing about it on the blogs, do we index Twitter? No.
But can you change the meaning of the word if it's stuck in a system?
Yeah, okay, so take the word like bra. If we would now decide that bra now means cow or something, and we all start to write bra instead of cow. If we were many people, because this is a quite common language, but the system would learn that meaning. Because it learns all the time.
It also forgets.
Yes. So what?
Type shit for English, but for Swedish and see what comes out. I mean, that's not something that you will enter by just thinking into some.
So here we have some.
For us, good.
Quite happy smiling. Happy smiling. Oh, what happened? What happened? So you have to. You know, you're right with people? No, away from coding. Yes. So the workspace doesn't only learn like normal words, it learns multiples. Looking at emojis too.
Looking for social data.
So I think in this feed it's both social and news.
Because some words are social and different meanings than
Yeah. It's one of the things that we're thinking about that we should expose only social data and news data separately, because it would be very interesting to see different associations, for example. This is one of the things that we do. If customers are interested in how people perceive the brands, for example, it's not really interesting to index news media, right? So they know that. It's only interesting to index social.
And you said the same intermental thing, but for each specific language. You don't have it as being
No, so what we do a pre-processing step where we do language identification. So if the language identifier says, okay, so this is Swedish, we feed it into the Swedish word space. But it's not perfect, so that's why we get controls. And Jimmy has this nice idea on how to use his models for language identification in just the model. So see if he's a genius or
okay, I like to hear all the one more question.
Just a short question. I mean, looking at the business, do you have any business aspect on this one?
I'm not sure. We don't have customers who stand in line outside the door waiting for the lexicon.
Yeah.
No.
No ideas at all?
We have ideas.
Okay.
We have ideas on things that we could do with this, but we do it mainly to expose our technology because we think it's a very good example of what we can do with this types of technologies. So the business aspect is a bit fascinating.
I think it's a very good idea to invention something before you sell it. It's a definition of the product.
Yeah, that's good. Thank you very much.
I think, I don't know, do you want to have like a 5 minutes break or? Okay. 5 minutes and then we start. Okay. We'll start.
So yeah, thank you for the nice introduction. I'm just a master's student in KTH, so I'm in this really nice program for EIT ICT Labs, which allows me to study in 2 places. So I'm here in KTH and in Aalto University in Finland, and I'm working with natural language processing and text analysis. So you all, or many of you might know the saying, "You shall know a word by the company it keeps," which is quite a nice idea and quite an old idea. But it's true to this day, and it's actually also one of the most successful ideas in modern statistical natural language processing. And the idea is basically, if you take the word banking, then and you see where it occurs, and it's similar to what Magnus was talking about, the word government and the word debt, often connected to banking. Also the word crisis, apparently. But yeah, so you can assume that these words represent banking. And as you saw in the other talk, you can imagine or you can represent words by vectors. And vectors are not really that fancy, right? You all know it from school. They're just directions in space. But you can do math with them, which is quite fun. So if you have the red vector and the purple vector, you can get the new direction from one vector to the other. And yeah, what we actually want, and the big goal of what I'm doing in my master's thesis, or one thing that I'm using a lot, is these representations of words by vectors. So these numbers are representing linguistics. And then in 2013, there was a paper that actually got a lot of attention because people found this interesting similarity, right? A vector is just a direction in space, but if you look at the vectors, then you see that the vector going from man to women is quite similar to the one going from uncle to aunt or from king to queen. So that's quite interesting because that's what we would call femaleness or gender, right? And if a computer can do that, then, because it's just a direction in space, I can take the vector going from men to women, and if I attach that to king, I end up at queen. This is a bit simplified, but the idea is the same. But if I have this, I can do these analogy puzzles. This is just repeating what I just said. Vectors are directions in space, and they encode certain relationships. So gender being one of them. And I can do this analogy puzzle. So man is to women, as king is to queen, which is ridiculously easy for us. But with this model, you can actually also do it in the computer. And this is, for instance, part of the SAT scores. If you want to go to college in the United States, you have to do these puzzles, which are part of sort of intelligence tests going to college. So that's quite exciting. But it's not just about gender. You can also do it with plural. So there's one direction going from king to kings, which is similar like the direction going from queen to queens. And that's quite exciting. And I hope you're not just one of the people who already heard this like a earlier time. I don't know, who hasn't heard this already? So another direction in this space is the one which could be the capital vector. So you go from China to Beijing, and that's very similar like the vector going from Germany to Berlin or Portugal to Lisbon. So these are different things that are part of this vector space. And they're all part of this tool called Word2Vec. And Word2Vec is both a tool and these two approaches to calculate these vectors. And I'm going to talk a bit about that. So the paper that it's based on is called Efficient Estimation of Word Representations in Vector Space. And I'm going to link to that in the end of the presentation. I'm going to share the presentation with you. But basically, it was developed in Google by Nikolov, Sutskever, Chen, Rado, and Dean. And it was not that old, so it's from 2013. And it's very easy to use because they make the tool open source, which is awesome. So you can take any text corpus you have as input, and then you can produce your own word vectors. So you have your numbers representing linguistics and all other words. And then you can play with them. So, for instance, if I add the word for Sweden, then the most similar words are actually Nordic countries. So that makes a lot of sense. The word Sweden is in a similar context as Finland, as Norway. It also not always works that well because I actually did this with quite a small corpus. It's only 100 megabytes. There are much, much bigger ones that are even freely available. So the floorball federations might not just be that representative of Sweden as a whole. And another interesting thing is that the airport of Helsinki, Helsinki-Vantaa, based where the airport of Helsinki is even higher than the adjective for Sweden. So this is not perfect, but it has some really interesting properties, and I'm going to show you how to actually use them. Similar example for Harvard. So you have both other elite schools, you have the place where Harvard is, and you have PhD and professor as concepts that come up as the most similar. Because, so this is just a similarity measure, is the cosine distance between the two vectors. So again, the word meaning and the relationships between the words are encoded spatially, and there are these two ways of doing it. There's the continuous word approach and the continuous scriptgram, and it's both part of the paper. So when you have the tool, the goal is to get these word representations, and the means are basically using a neural network. So this talk is a bit too small to actually explain what a neural network is. It's a bit of a topic in itself. So let's just assume this works. It does work. And treat it like a black box. But I still want to show you how approximately these vectors are trained. If you do the continuous stack of words, and I guess many of you know stack of words, so here again, we don't care about the order of the words. It doesn't influence the projection, but we try to predict the word here at the side by the other words surrounding the word. And we can play with this size. And this is what Magnus was talking about. So they take two from each side. You can do it, you can play with it. And this approach is a bit simpler, it's a bit faster, and thus more appropriate for larger corpora. The other way is skipgram. So here you take the word surrounding the word to represent the word. In the other case, you do it the other way around. You take one word, and then you try to predict the other words around it. And you use this as the measurement in your neural network. So you change the vectors accordingly to maximize the classification of the word. And this is better for word vectors. It's better for frequent words, but also slower to train. So why this is awesome for me, or maybe also for you, hopefully, there is a fast open source implementation, and you can use this as features for your natural language processing tasks and other machine learning algorithms. And one really, really cool thing is if you do this with English and if you do this with Spanish words, and then you have to adjust a bit. So it's, again, the reality is not as nice as it looks here, but still it's quite a cool thing. Because this allows translation. So you can take the vector for the word horse, and then you have these numbers, this direction in space for horse. And then you take this direction, you go to the Spanish word vector space, and then you look at that point in space, and you find the word caballo, which is the Spanish word for horse. So you can actually do this, like, it's just a dictionary lookup, but it's still very interesting. And this is another paper by Nikolov, where they try to do machine translation using this. Another thing where this is applied with recursive neural tensor networks is sentiment analysis. Because in a naive approach, and maybe some of you already tried this, if you have a sentence like, this film doesn't care about cleverness, wit, or any other kind of intelligence humor, and you just look at words, you see, okay, humor is a very good word, intelligence is a very positive word, care is a very positive word, but actually this is negating it. And this is only possible because of these neural networks, so that's quite exciting. It's not directly associated with word select, but I still wanted to share this with you because it's a similar approach. Same with this one. Here they take pictures, descriptions of So you have a Flickr data set with a lot of pictures and a lot of descriptions for these pictures. If you want to have a neural network that can get one of them and predict the other one, which on the one hand is what Google does if you do Google search, right? They give you a guy on a motorbike. But if you can do it the other way around, pretty awesome, because you can make blind people see. You just show them the picture and then you read them what's on the picture. You can read them. Yeah. So this is really exciting. And I think it's good times to be interested in these kind of things because there are a lot more cool things coming. We're talking a bit more about practical things on how to use and compute these things. So you have a variety of options to do it. You can use the original C code from Google, which they released. There's a C++ version, Python version, there's Java, parallel Java. And you can also do it on the graphics card. For this talk, I'm going to use Python, mostly because I use that for my thesis, also because it's fun and very easy and should be quite readable for people who never saw Python. Nice thing about Python is that it comes with this library called gensim, which provides topic modeling for humans. And on this website, you have a lot of really good tutorials as well, which explain things in far greater detail than I can do here. But if you have everything set up, it's really that easy. So you just open the vectors you have trained, and then you can go through the words you have. And if the word is in the model, because not always all words are in the model, then you can print out the model. So this is really like the essence of what I'm going to talk about. But how do you train them? Again, this is quite easy if you use Python and gensim. So you have just a bunch of sentences, and then you can put them in, and then you mostly need time, because this can take quite a while. Not with these two sentences, but this is not really used for modeling. If you're going to use it, this is a bit like the Python thing, you should do it like this, because in the other case, it keeps all the data in memory, and if you have a lot of data, this is much more nicer. It's called an iterator in Python. But actually, this didn't work for me. I had to do it in C. I had to do it the hard way, which is okay, but it didn't work on macOS either. So the original tool, I made it work, and you can use this on GitHub if you want to. And then you just do make and run these two scripts, and then you get these two vectors, because that's all you actually need. So you just have this one file, and you put it into the Python library, and then you can play with it. But I still haven't explained to you why it's cool to play with it. I'm getting to that. 1 second. You can also use these vectors provided by Google. And they trained it on 100 billion words. They're incredibly huge. They're like gigabytes, even if they're compressed. So I can't run them on this computer, unfortunately. But if you want to do like a larger thing, and yeah, you can just get them for free, and I think it's pretty cool that Google is providing them. They were trained to skip their architecture. And then you can test your model. Also, this is also gensim, so gensim has this accuracy, and Google provided 20,000 examples of these. King and man is to women, as queen is to king, and all these kinds of things. You can use this. So this is what I'm doing with it. I took an entire book, in this particular case, a book called The Power of Habit, and then I calculated the most frequent words, the most 1,000 most frequent words, got the word for that vector for it, and then projected it down. So I have what I call the bird's eye view on a text. And this is, we use this for editors, and they play and explore text with it. So here, for instance, you have this one space, or this one section, which is about disorders, obesity, something medicine related. Then you have one that is marketing, corporate advertising, and this is all the same book. And then there's also laboratory experiments and studies of researchers. And this, for instance, is just my own thesis projected down with this dimensionality reduction tool. So you have Microsoft Linux, Wikipedia being close together, distributed Unix. And I actually built a tool for this. So these are two articles about Spotify, one from the Wall Street, one from the Financial Times, the other one from the Rolling Stone. And the green ones are words that are in both, and then red is just in one article, and blue is just in the other article. then you can play with it and explore it a bit. And yeah, so you can move around and just understand and compare text with this. This is how I mostly use it as part of my thesis. Yeah. So if you want to do this, there are pretty much just 3 steps. You have to find the word embeddings, you do dimensionality reduction, and then you output it in a nice format. So talking about the first step, this is pretty much all you need, and most of it is not really that useful. So let me blend that out. So I'm going through all the words, and then I have the set where I keep track of the words I already have, because I only need the vector once. And then I'm sorting out the most frequent words. So I have this list of the most frequent words from Wikipedia, 3,000 most frequent words. And if it's not a frequent word, because the idea here is, if it's a frequent word, it really doesn't tell us much about the topics, and I use this to understand more about the topics and text. And then we just collect them. With that collection, we now have a bunch of 300-dimensional vectors, which I really can't deal with in my head. So they're really nice technologies, like techniques, that take these huge vectors and then project them down so I can show them in a 2D way. And one of them is called t-SNE, so it's a stochastic neighborhood embedding. And then there's this paper, which is very nice, but actually, frankly, I never read it, because there's a really nice Python implementation which I can use. And you can just install it. It's part of this really, really nice other library called scikit-learn. And just to give you a feeling how easy it is to use this, this is all you need. So you put the vectors in, and then this first line is even just because of some bug, and I think they fixed it by now. So the essence is this. You just say, okay, whatever I give you, just give me 2 dimensions, and then you do fit transform. So fit trains the model, transform changes the vectors. And again, you have these, the clue here, of course, is that the 2D vectors are still as similar to each other, or almost as similar to each other, as the 300-dimensional vectors. And that's why I can project them down. And to visualize it, I use JSON. So again, this is quite easy. I just get my vectors and my labels in, and then I just collect them. I'm going to share this in the group with you if you want to play with this. But this is pretty much how it looks. You just get a lot of coordinates, and you have all these words. And then there's this really nice library called v3.js, which is a JavaScript library. And with that, you can do all kinds of visualizations. I hope I wasn't too fast. So this is another thing I quickly want to talk about in the end, because this is the bag of words model on the left. And you can see, for instance, the word Turing. In these cases, it's connected to the Turing machine, so it's non-deterministic compatibility. Right? With the dependency one, Magnus just talked about quickly, which is another model, which is another nice Python library, you get names of other researchers because it takes the part of speech taking into account. It's a supervised model. So the same for Florida. In a simple way, and this is what we saw earlier as well, you look just at the context, but if you take and train these vectors with other information, you can go from Florida and just see other US states. So this is just to show that there's a lot to play with, and also it very much depends on what you're focusing on. So with that, you don't have to, but I thought, like, so is there anybody here that thinks that this might help him or her? Or if you have any other questions, let me know.
Just a small question. So if I understand correctly, it's a neural network to predict the word in the middle with 2 words in front of the word and behind the word. And so that's the model, and you have 1 neural network per 4 inputs, or you only have 1 neural network.
It's up to everything. It's up to you. For instance, in this particular case, they had the window size of 2, And I think this means 2 to the left, 2 to the right. And then you can do it with 5. And it all goes back to this very first slide.
Yeah, what you can see here, it's more what you feed into the network. The network architecture is completely the same. The only difference between these...
It's the same parameters in the model.
I mean, basically, you just say, give me, you know, here's a certain dimensional vector, like let's say 500 dimensions, 300 dimensions, whatever. Initialize some random weights, and now just start optimizing it until it starts making sense, and I can do this prediction task of predicting the next word or the words around it or something.
But the input layer with those token and like the window of +1 is 2.
Yeah, exactly.
And then you have the layers of the deep learning. That depends on the architecture, how you design it, and then at the output you will get the value.
But most of the, I mean, what is so exciting about these methods is like the neural network is not very exciting. It's a very simple model. That's why everybody can run it on their laptop. And they're generally the same. What is exciting is more the kind of intuition about what do you feed into the network and what do you do very simple prediction tasks, and you actually get really exciting results about them, much more meaningful than what you actually predict with the kind of knowledge of, you know, human language.
Yeah, I was just going to say, so here you can just configure how much you let in, and then intuitively, it is just like how many of these words you take into account. Right? So if you only look at 2, then you only look at these 2, you can go as crazy as you want. If you increase corpus size, then what phenomenon you see? I mostly use these for visualization tasks and to compare different sources. So I'm taking a book and compare it to a summary and use it from a visualization point of view. I haven't much experience with that, so if anybody can do it,
In the slide that you showed the visualization of using two different sources and combining them. Can you see it again?
Yes,
Just
you mean the video?
I'd like to look at the example and see when they combine the two sources.
Oh yeah, sure.
Yeah.
And if somebody wants to code, you can let me know. The problem is, I don't really think this code is so easy and intuitive to just release it. But if you want to play with it, just let me know. And this is not so nice because it's just with these articles, and they are quite small. So it's much more fun if you do it with actual books or book summaries. Yeah, but this is all I talked about in the talk. So this is clear that we will work with that with the and I think at one point here in the video, you for instance see the month. So here September, March, they are close to each other. But unfortunately, there's not like this really nice intuitive example. Like I just really like this one. I mean, everybody knows about the news go together, and then with this one and the book approach as well.
And another question: have you tried? I know, like one book is a small size, data size compared to very large corpus. But have you tried to see the result from one chapter to the whole book and from another chapter to the whole book?
No, not yet. No, so far, it's more about if we we want to use this to assess how somebody is good. Do we capture that? You know? So that's the goal. And plus, you want to just like have an exploratory way of exploring the book. Because in added sense, you can see the book from above.
Any other question? You said that you couldn't use the Python, you have to use the C version. Does it have any like practical reason, or like you know? I've never used them, so I just asked you to share your experience. That's why
I didn't fully remember why, but like I remember I just did the C version and that worked. I think there's no speed improvement actually because the Python version is quite optimized and uses a lot of tricks really fast, like really fast. So I maybe it worked. I had to do it initially, and then I just kept doing it because it's quite easy for me. It's set up now like that. I think practically there's no advantage. It's whatever fits the
The Python version is actually faster a bit, like 30% faster than the C++ version, and also it gives actually better accuracy. Maybe they fixed it because the word2vec, you know, see it is being updated. There's like different versions. It might be fixed.
Okay. Any other question? So thanks a lot for you. It was really nice presentation. I really enjoyed it. And I think we can again have 5 minutes break and then get back to Jimmy's presentation. Thanks.
Just for 2 seconds.
Yeah, we have a really I have a very this project. Yeah. So I tried to so now I have chapter 11. Yeah. So I have yeah. So it has been really tough to work with someone But yeah, I talked about the presentation. It would be nice that we like, you know, keep these conversations, find interesting people, and then because I remember it's like really close by your office. Well, we are at the beginning of the yes. Yes. No, it's not so that it's close to yes. Yes, we are like on the very south of Rotterdam. Yeah, we
No, no, no,
yeah, okay, it's fine. Actually, we have very much we have software at the end of each quarter, so nice now that I know. It was very yeah, it was like you know, I have also studied in a different culture. I come from Nigeria. So, like,
Yes, so it comes with a lot of other things.
Så jag tror att det var 10 månader sen var det hon var från Tyskland. Jag fortfarande säger att jag var den enda svensk. Precis. Jag tror förra året så var det någon tjej som var svensk. Så jag kan säga att jag är den enda svensk. Ja, men det var liksom när det först var någon visst ibland programmering först kanske var matematik jag hoppade några sen kom det musik så var det också mycket musik framförallt sen kom programmering jag hoppade många
det är samma med
kan man göra det är mycket logik det låter lite jobbigt det där. Sure.
Man kan
I'm bra. Så jag är också vet innan språk så läser lite matte. Lite så. Så det är helt bra. Ja.
ja.
Is everybody here? Are we going through it?
Ja. Men jag tror det där ska separera. Så det kommer men det
I think now we can have the third part, which is about the practical part, and I'm very curious to know about it. Thanks, Jimmy, for putting things up together and also for sharing them before the presentation.
Cool. Everybody here? My name is Jimmy. I'm working here at Gavagai. I'm mostly the one who manages the support together with Nina here. But I'm also an editor and do some data science stuff whenever I get a chance. And I'm also bothering Magnus all the time with questions about distributional semantics. So he's my source of knowledge here. And today we will be talking about a library that I created last summer when on my friend's lab in Uppsala called gensim, which is a Python library for exploring distributional semantic models in different ways. And this isn't the first one, and it won't be the last one, but the reason why I created it was mostly because I like to create my own stuff, but also because I wasn't quite fond of all the different models that were out there, like space or I don't know, there's one called dissect. So this one was meant to be fun to use. It was supposed to be easy to extend with new different functions and models. And it was supposed to be easy to use together with Python notebook and those kind of data scientific tools that most people. So let's import into the topics. Right, so first an overview of gensim, later some comments and operations. Lastly, we'll be looking at some kind of case study, let's call it case study, about a paper that's almost got, well, they got 100% students. It's an new test known as TOEFL, which is a very popular test out there for testing the quantitative marks. And this is basically how you do a communication agent using gensim, if you wouldn't use it. By the way, I've heard some people have been having troubles installing this. Please let me know and I'll see if I can. You define a model, in this case a coherence system, which is the typical vanilla kind of model that Magnus was mentioning before. You choose a corpus. In this case, we will be using UKWAC and 100,000 lines of it, which is about 6 million words, I believe. And that's, no, 100 million words. And that's about maybe 1/50 of the entire size of that corpus. It's basically a large collection of logs. Also, we will be using a window size here of 2+2, which means that we would be looking towards the left and towards the right of a focus word. And the reason why we're using this is you can find out by reading Magnus' presentation, very interestingly. But basically, it tells us that we will be looking for paradigmatic native. That is, we will be looking at, if we have this word, what other types of word can I change that word to? And understandable. Also, to try to think that we will be looking at words that have at least a frequency of 50. And this is what one would look like if we look at some sort of context of it. If we would only look at these types of words, we would be getting these types of frequencies. So this is no more than a frequency. How often does U occur in relation to gamma in a context of 2? 6 times. And we can apply some different operations on this. We got the most common operations, like the way I was talking previously about. Here, we are creating a positive pointwise mutual information matrix from this previous one. This means that we're doing the pointwise mutual information and we are removing all of the different negative values. We will be looking at that later. Also, we can look at diverse neighbors quite easily. Here we have all the different neighbors sorted in the sort of distance-wise of blue. And we figured that we get pretty nice neighbors here. We get some great stuff down here. But that's basically what happens. You enter a word, you get back the neighbors. And how do you evaluate this type of model? Well, I mentioned total before, and this is what total looks like. You get the word hasten, and you want to get back the answer for what is the synonym for hasten. And this isn't just difficult for machines, this is difficult for me as well. I have no idea what tranquility means. I don't know if you do. But the answer says it's pre-semantic. We can look at different other kinds of work as well. We look at make there, for instance, and know that make means all various different categories. But in this case, by the candidates we have earned, that is. Yes. Could you please go on? Oh, yes, of course. That's better. Okay, cool. It's so smooth. Okay, and so yeah, so we got tranquility. Peacefulness, we got make, it's earn in this instance, and we want the DSM to understand this, or like find this somehow. And the way that a DSM, that is distributional semantic model, does this is by basically asking what word of these candidate word is the one that's closest to the focus word. And using this on this basic model that we built before and that we've been looking at, we can see that it doesn't perform very well. It's almost half of the answers correct, which isn't. It's better than random because random would be about 25% since we got 4 different options. But still, it's not very interesting, or not. It's not a good result. And the reason for this is that we don't have any weighting yet, because we have been looking at pointwise mutual information for that basically says all words like and or and if that occurs all over the place. Those aren't that important for the actual meaning. The words that are important are the words that occur in a specific context. Like if we're looking for the word cat and the word dog, if it's occurring together with breeding isn't used very often, but in the case of maybe cat and dogs, it's used more often. So that's a more interesting word, and we want to weight that up. And that is what the pointwise mutual information does. It weighs down the words if and it weighs up these weighting. And when we apply that, removing all of the negative values to increase the sparseness, and for some reason it does it seems like it decreases the accuracy even more. We get 82.5
which is much better. But it's still not those 100%, and I think it's worth that we won't get it today because we don't know. But we are using the same data set as those that are using that we're getting to later, but 100%. Only we only using like 50 of the size to make things viable and not 100. So to get things even further, we need to use something called similar value decomposition, which is what they have been using, and also what the LSA makers is using. How many here have heard similar value decomposition before? Okay. So what's it's a difficult topic to explain, but basically you can look at it. If you got a matrix that has all of these different vectors that defines a vector space. A vector space have all these different vectors, and they point in different directions, but they will always point in like some directions more than other directions. And if you look at the first direction, like the direction that they point towards the most, that is the direction which has the most variance. That will be the first eigenvector, or the first principal component in the single value decomposition. Now, if you do this a amount of times and place these as columns, you will eventually get an approximation of this matrix. So it's almost some kind of like a compression algorithm. It's like when you're saving a JPEG and you get to choose how high the quality. And the reason why we want to do this is because traditionally, when people have been using this, they've been thinking of, okay, so we only want to look at the variance for like the directions where it's most that has most information. We should be the ones that are the largest. So we look at the 200 largest eigenvectors of the components, because the rest of them, they're mostly noise. They don't add anything, actual information to the data, so we don't need them. And people were doing that, and in the case of LSA, it improved results incredibly because of how they have structured the data. That makes sense for work. But in this case, we're actually performing the SNE, which takes about a couple of hours. This is a very heavy operation, which is why I don't like it. And you get back all of these different vectors, which are much more dense than the previous ones. We actually don't get that much better results compared to the one. If you were supposed to do the same thing on the LSA, you would get a much higher improvement. But here, actually, you still are on the same level. And the reason for this is probably because of that we have already weighted the matrix before. I would say why we're doing this, by the way, is because there's a paper by two people called Gavagai and Gavagai, and they are doing this stuff. So we're basically re-implementing it. And what they realized was that if we don't look at those first 200 single value, like the first 200 eigenvectors, but we actually remove them, we get much better results. For some reason, the results get much higher. And if we were to use all of the data they were providing, this would be up in the 98%, or perhaps even 100%. So because of that, let's go down. We are just not there. So we get 86%, and when we were doing the first 200 eigenvectors. So the previous assumption that all the noise is collected in the lowest eigenvectors is apparently wrong, because when they started to add noise to the model and they looked at here's noise. For instance, there's 8 point some kind of unit noise, and here they're removing the different dimensions that I was mentioning. And here is the performance. And as you can see, despite them having a lot of noise down here, which really makes the model completely random, once they start to build up here towards about 100 vectors, they start to get up to the same values again. That's better by time. Yeah.
So when you say to remove the first 100 dimensions, by the first, you was first indexes or first according to ascending or descending?
Oh, when you're applying the single value decomposition, you get back singular values that are ordered. And when you order these given, so when you order these, you get some eigenvectors that are larger than other ones. And then you're just cutting them up of the matrix. So, and that's what I'm doing here. We're excluding this dimension, but just cutting them up. And they get back to the previous results, which seem to show that perhaps there are a lot of noise in those first vectors as well. And they even hypothesize that these are the vectors where that have most of the syntax of the language as well. Perhaps that's the reason why. But I haven't actually seen any results. And that's it. Again, we were supposed to go use the homework paper to get about 100%. And that's how we can use it's quite simple to actually try to reproduce albums. You just use the concurrence DSM and you apply some of the different functions, which should be quite similar to people who are used to dealing non-pi or sci-fi quickly. Everything's on the same time. If you have any questions about how to install it or how to use it or find something like this,
we were trying with some legal documents or criminal investigation documents in the corpus.
I haven't tried with legal documents. Has someone here tried with legal documents?
Yeah, we've done some legal documents. So you get time clusters conform to language in legal documents. It can be quite helpful. So e-discovery is a big business in the US. These type of laws are used for it.
So is there anything on the roadmap of UI DSM stuff you want to put in there? Or?
Oh, I want to put those in there. Right now, I'm putting stuff in there that I myself need because it has been a personal project. If other people are starting to use it and they have some kind of like stuff that they need to put in there, I will of course be those into account as well. Right now, I will be focusing on different evaluation methods. Right now, it's got TOEFL and another one called Simlex, which is kind of similar to TOEFL, and with that you rank different associations over instead than just providing one single synonym. There are different evaluation methods used by Nicola and Goldberg and those as well. I want to look further into those. And I'm right now working on language identification, so I won't be putting anything out of that in there because that hasn't been. Yeah.
So what was the data set? Is it like how?
What kind of evaluation data sets? It's a standard data set that you can get by. It's not actually open. I still put it in my library in a binary form, so when you're using it, you can still get results. But basically, it's a standard text that has been used since '97, I believe, by some guy, and people are starting to use it, and basically it's ubiquitous when you're doing these kind of models. Quality improvements using different ways. So you will always find it.
It was curious to see if you have learned model from English editorial articles and then try to answer a question test. What the biggest score of the accuracy. I know, like, when the accuracy is going there, yes. Just if you have done that.
No, if I've used an actual total test. I believe this is an old total test to begin with. I haven't actually been looking at the newer ones to see how that's going. That would be interesting. But I'm not sure if they actually release those. Still an interesting point. Yeah.
Questions?
Thank you.
Okay. So I think we can say that we are done with the presentations. So still lingering time. But before that, I'd like to ask again. First of all, if you have any feedback on the meetups, just let us know. And then the other thing is that we had very nice I think presentation today, just because of having very good volunteers. So if you feel that you have something that you want to share with others, just feel free and let me know, and just organize it, and we learn something together. Because I'm learning a lot. Yeah, that's about it. If you have any questions related to the meetups in general.
Do we know what the next one will be about?
Well, good question. I don't know yet, so that's why I'm asking everyone. We had a conversation with Rolf about the second session, but we said that probably later, right? Maybe.
Yeah, we can discuss. Yeah, exactly.
So, do you have any suggestions?
Sorry.
No. Any suggestions? I mean, we can think about now. Yeah, just write your suggestions and we figure out what would be the next one. But so far, I think I can proudly say that we managed to have 2 meetups per quarter. So next one will be soon. Yeah. But yeah, let me know. I mean, I'm not that expert in NLP and learning, so I don't know many of yours backgrounds. So just feel free to share your experience. Would be really nice. Thanks for coming. One more thing, I think we can still have 9.